Modern data centers handle multi-gigabit throughputs. Pushing millions of packets per second requires precise architectures that dictate how data propagates to its intended destinations. The default mechanism for most user-driven applications is Unicast. It operates on a strict one-to-one delivery model, a single center transmitting data to a unique, specific receiver. At the hardware level, a network switch extracts an arriving frame's source MAC address, logging it in a CAM table alongside its physical port. For subsequent frames, the switch cross-references the destination MAC, forwarding data only to the designated port, preventing unnecessary bandwidth consumption. Because the communication is strictly one-to-one, the sender can track acknowledgements and perform precise flow control. Unicast provides the reliable, stateful connections required for discrete user sessions. However, an individualized architecture creates a structural bottleneck during mass distribution. Consider a core server attempting to push a high-bandwidth live FAO stream to 500 individual nodes simultaneously. Using Unicast, the server must generate 500 identical streams, increasing bandwidth demand linearly with every new receiver. This redundant data quickly saturates the server's uplink or core network link, leading to physical failure even while downstream segments remain underutilized. Solving this bottleneck requires a pivot away from one-to-one models toward multi-point delivery methodologies. To maintain multi-gigabit speeds, network architects must deploy specialized delivery methods that fundamentally change how traffic propagates across the fabric. Broadcast transmission is the most direct alternative. It is an indiscriminate one-to-all method that targets every device within a Layer 2 domain using the all-ones MAC address FF:FF:FF:FF:FF:FF. This inefficiency is a requirement for IPv4 initialization.
Protocols like ARP and DHCP depend on broadcasts for unconfigured hosts to discover resources and announce their presence on a network. The performance penalty occurs at the endpoint. Unlike Unicast, every host passes broadcast frames directly to its CPU. Every node interrupts current tasks to evaluate the payload. In large domains, hosts waste CPU cycles evaluating irrelevant discovery packets. On chatty enterprise networks with hundreds of nodes, this background noise creates a persistent degradation of system performance across the entire segment. Indiscriminate delivery transforms a necessary discovery tool into a heavy computational tax on every device. The most catastrophic manifestation is the broadcast storm. Caused by a physical cabling loop, frames are endlessly replicated, causing a total collapse within seconds. To resolve the outage, analysts use packet inspection tools like Wireshark to determine if the storm is a Layer 2 hardware loop or a Layer 3 routing loop. This capture isolates a circulating packet. In a Layer 2 physical loop, hardware simply reflects the exact same data. The IP identification field remains static. As packet count increases, time to live and IP ID values remain frozen, confirming a physical loop. In a Layer 3 routing loop, the TTL instead decrements with every hop until reaching 0. Distinguishing these two states through packet-level analysis is the only way to determine if the failure lies in the spanning tree configuration or the routing protocol. Multicast serves as a selective middle ground. It provides broadcast reach without universal CPU overhead, utilizing dedicated Class D IP group addresses for interested receivers. This model is built for conservation. The source sends only one stream, and network routers replicate that stream only at the points where the path branches toward receivers who have expressed interest in the traffic. This interest is managed by the Internet Group Management Protocol, or IGMP. It acts as the control plane, allowing hosts to dynamically join or leave logical groups. However, because switches cannot learn a multicast group address, they naturally flood the traffic to all ports like a broadcast. IGMP snooping prevents this by allowing the switch to listen to IGMP joins and build a precise Layer 2 forwarding table. Multicast is a sophisticated compromise. It preserves core bandwidth, but relies on protocol-aware hardware to keep traffic from spilling into unintended segments. To switch these frames at hardware speeds, the network must map the Layer 3 group IP to a Layer 2 MAC address deterministically. Mapping 224.1.1.1 faces a constraint. The IPv4 address has 28 variable group bits, but the MAC prefix 01005E leaves only 23 bits available. The first 5 bits are discarded. The remaining 23 bits are appended to form the final MAC. 01005E 010101. This loss of 5 bits of data means the mapping is not unique. 32 entirely different multicast IPs will all map to this exact same Layer 2 MAC address. This overlap requires network engineers to meticulously plan group assignments to avoid unintentional traffic flooding in high-density environments. The transition to IPv6 represents more than an expansion of addresses. It's a deliberate architectural decision to completely eradicate broadcast as a transmission method. The functions previously handled by the noisy ARP protocol are now managed by the Neighbor Discovery Protocol, or NDP. NDP uses solicited node multicast, calculating a specific group based on the target's IP. Instead of flooding 100 nodes, the query pings only the target. IPv6 refines this through scope fields, permanently confining traffic to boundaries like link local, preventing leaks into the wider network. IPv6 replaces domain-wide interruptions with precise, mathematically predictable logical extensions. The final delivery method powering the global internet is Anycast, a one-to-nearest logic. Anycast lets dispersed servers share a single IP address. Routing protocols automatically funnel users to the closest active node. If a server fails, the network instantly reroutes users to the next closest node without changing the destination IP, a standard architecture for CDNs. Unicast, Broadcast, Multicast, and Anycast represent structural compromises between bandwidth utilization, CPU cycles, and geographic latency. By mastering these protocol constraints and bit-level mechanics, network professionals transform raw data floods into highly deterministic and scalable digital infrastructure.